Okay, so let's start. So today we'll solve two questions from functional analysis. These are questions from 2000 Gate 2021. One is question number 33, one is question number 35. Okay, so let me first play the question number 35. Okay, so today we'll solve Gate 2021. This is a question from functional analysis. It's question number 35. Let L1 be the sequence space, means which are all such sequence which are summable. And the norm is given by this. Then consider the subspace of L1, all such sequence is that n times xn, and sum from n to 1, n equals to 1 to infinity is finite. Then we are defining a linear transformation from x to L1. T of x of n is given by n times xn. Then you have to check four options that T is closed or bounded or not bounded, T is bounded, neither closed nor bounded, T inverse exists and is an open map. So which one is correct? You have to check. Okay, so in order to solve this is the NPTEL reference. This you can check. Okay, let's start solving. So L1 is the such sequence space such that these are summable. And X is a subspace of L1 which is given that all such X in L1 such that n equals to 1 to infinity, n times mod xn is finite. Then we are defining a linear operator from x to L1 which is given by T of x at the point n is given by n times xn. Okay, so this is the linear operator from x to L1. Note that why this is well defined. So we are taking a vector from x and we are sending it to nxn. For all such element, if it is in x, then xn is finite, means nxn is in L1. So therefore this is its nxn is lies in that space L1. So therefore this is well defined. Okay. So now we have to check that T is closed or bounded or 1, 1, 1, 2 or not, or open map or not. First we will show that T is not bounded. This is, T is obviously linear. Yeah. So now note that T is not bounded. So this is easy to check. So why? So we take that function. Suppose take at the nth point sequence, take a sequence which is at nth point it's take 1. Then if you plug it in T, it will give n. So and the norm of this is n, right? So therefore that can't happen. Okay, so let me write. T is not bounded. Why? So take define First take a natural number. Gn at the point we are defining a sequence which is 1 if n equals to capital N and 0 if n not equals to capital N. Right. So what will be the norm of this? Note that X is a subspace of L1, so there we are also giving the L1 norm. So Gn is, note that Gn is in L1, X. Because it is only non-zero at 1 point, so it will obviously satisfy this condition. And what is the norm of Gn? So this is only 1 point, it's take the value 1. So its norm is 1 because at n equals to n it will means L1 norm. So basically summation n equals to 1 to infinity. And this is only 1 at n equals to n, it will be non-zero. So this has norm 1. What will be T of Gn? So T of Gn is n times Gn, right? And okay, now what will be the norm of T of Gn? Norm T Gn. Okay, so this is n, right? Because if n not equals to n, capital N, then this will be 0. So this is at and the point if n is equals to, so this is n. So norm of T Gn, L1 norm. So this is so only at the point n it's 1, so this is same as and otherwise it's 0. So this sequence is basically if n equals to n and 0. So therefore n equals to n, it will take the value n. So this is norm as n. Okay. And so can T be bounded now? So note that T is bounded means T of G should be less than, or T of X should be less than C times norm X for all X in that space X, right? If T is bounded. But this, note that, but there does not exist any C positive such that norm T F is less than C times norm F for all F in X. Why? Because if this will happen, then we put F equals to, because because if this happen, Then, so for f is all such f in S, gn is in x, then t of gn will also satisfy this, or you will get n is less than c times and this norm is 1. So n is less than c, but this cannot hold, right? Because you can, n is in natural number. For all n, right? But which is a contradiction. Because we can choose this n to be a sequence, so this is for all natural number. So means if you take this capital N to be large, then it will be only non-zero at that point, so there it will take the value, it is n. So basically it will be this capital N, right? So at the point n equals to n, we can write also capital N. Which is a contradiction. So which implies, means there cannot exist a positive c so that this will happen, so which implies t is not bounded. So t is not bounded. So this linear operator is not bounded. Now we have to check that this is closed or not. Okay, so let's check. So now we will show that T is closed. So what does the mean a operator to be closed? T is closed means what we have to show? So to show if Fn be a sequence from X, and so Fn be a sequence which, suppose Fn converges to F in X and Tfn converges to G in L1, because T map from X to L1, then T of F equals to G, that we have to show. So this means that T is closed. So if Fn converges to F and Tfn converges to G, then Tf should be equals to G. So this we have to show. Okay. So first note that convergence in X will imply pointwise convergence. Convergence in X imply pointwise convergence. Why? As you can see that f of n, this is always less than norm f x norm, which is L1 norm. So this is always true because this is the summation of Fn, right, for all n. So if something converges in the x norm, then it will converge as pointwise. Okay, so convergence in x imply pointwise convergence. So now we can show that T of f equals to g. So then for all m in natural number, what is g of m? So g is L1 limit of T of fn. So this is the limit of n tends to infinity T of fn. So this is convergence in L1. Right, L1 limit. Now what is limit n tends to infinity T of fn? This is T of fn is, so T of fn is basically at the point m, right? So again this is convergence, L1 implies pointwise, so we are writing it, so we can write gm for each m, this will hold, right? L1 implies pointwise. Now this, what is this limit n tends to infinity? This we can write, this is definition m fn m, this is definition of T. Now m, because this limit is independent, m can take it out, limit n tends to infinity fn m. And again we have shown that fn converges to f in x, and this implies pointwise convergence. So m, so this will converges to f of m. So due to pointwise convergence. And what is m fn? This is again T of fm. And this is true for all m in n, so therefore T of f is g. So that we have to show, which implies T is closed. Okay. So you have shown that T is closed operator. Now next we have to check the other option. Or T inverse exists. So for that we have to check this is 1 1 and 1 2. So what is T? Not T is from x to L1. T of xn is nxn. Note that by definition, what is it is onto, T is onto, right? Why? For any y in L1, define x to be 1 by n y. So this is for all n. Then x belongs to x, because if you multiply n it will cancel and y is in L1, right? And T of x will map to so it is n times, so it is y. So therefore T is onto. And T is, why T is 1 1? T is 1 1 means let T of x equals to T of y. So means T of xn equals to T of yn for all n in natural number means n xn is n yn, or n we can consider out, so xn equals to yn for all n natural number, so which implies x equals to y, so t is 1 1. So therefore T inverse exists. And so when T inverse, let S equals to T inverse, and it will be given by S x at n, it will be given by 1 by n xn. Okay, so T inverse exists, and now what we have to check next? T inverse exists and is an open map. Okay, so you have to check that T inverse is open or not, or S. So first, for that, let's check that S is bounded. So, note S is a map from L1 to X. S x at n is 1 by n xn. What will be Sx norm? X norm. So this is summation 1 by n xn. So this you can always write less than n equals to 1 to infinity mod xn, which is the L1 norm of x, right? So which implies S is bounded. So S is a bounded operator, and okay, so S is also 1 1 1 2 also, because T is 1 1 bijective also. S is 1 1 and 1 2. Now let S is open. So assume S is open. Then what happened? Let's see. So as S is a linear operator, this is bounded means this is continuous. So we have so this is continuous map which is bijective and which open. So there is a one result that bijective continuous map, its homeomorphism if and only if it's open. So let me write a result. A bijective continuous map is homeomorphism if and only if it is open map. Now here what we have? Here S is continuous as S is bounded and linear. And bijective, continuous bijective and open map, because we have assumed S is an open map. So by the above result, S is homeomorphism. Means, so S inverse is continuous, because homeomorphism means inverse map is continuous. Now what is S inverse? Therefore S inverse is T, which is linear map, so T is continuous, implies T is bounded. But we have shown that T is not a bounded operator, it's not bounded. So therefore our assumption is wrong. We have assumed that S is an open map, so this is not true. So S is not an open map. S or T inverse is not. Okay. Okay, so now let's see which option is correct. T is closed but not bounded, that we have shown, so A is correct. T is bounded, so this is not true, B is false. T is neither closed nor bounded, but T is closed, so this is also false. T inverse exists and is open map, but T inverse exists but this is not an open map, so D is also false. So only A is the correct option. Okay. Okay, so we have done the question number 35. Any question? Okay, if not, so let's move to the next one. Okay, so today we'll solve Gate 2021 question. This is a question from functional analysis. It's question number 31. So let L2 minus 1 to 1 be a Hilbert space of real valued square integral functions on minus 1 to 1. EQ with the norm, this is a square norm, means L2 norm. Now consider the subspace M, all such function in L2 from minus 1 to 1 such that integral of f over this interval is 0. Now let for f is defined by x square, you have to find the distance, means distance between f and the subspace M. 4 options are given, you have to check which one is correct. Okay. So in order to solve this is the NPTEL reference. This you can look into it. Okay, now let's start solving this one. So L2 minus 1 comma 1 Hilbert space of all square integral functions, and now M, this is a subspace of this one. This is a collection of all f in L2 minus 1 comma 1 such that integral minus 1 to 1 fx dx is 0. And what let fx is given, it's given by x square. To find you have to find the distance which is the infimum of norm f minus g, where g is from the subspace M. So this is the distance between f and the subspace M. Okay. So L2 is a Hilbert space, so it has a inner product. So for G and H in L2 minus 1 comma 1, how the inner product is defined? GH, this is defined to be minus 1 comma 1 to 1 GX HX. So this is a real inner product space DX. Now M we can view it some kernel of some linear functional. So let's define a functional. Define T from L2 minus 1 comma 1 to R. How it is defined? T of F, T of G is minus 1 comma 1 Gx dx. Right, so because it is in G is in L2, so it is in L1, so this is well defined, so it is integrable. So this gives some finite number, so and this is obviously linear. So T is linear functional. On L2 of minus 1 comma 1. Now what is the kernel of this linear functional? So look kernel of T, so it is all such G such that T of G is 0. And how we have defined T of G? So this is all such G such that integral minus 1 to 1 Gx dx is 0. Right, so what is, so this is also G in L2 minus 1 to 1, right, such that T of G is 0. Note that this is exactly the M, how M is defined. So this is the M. So M is the kernel of this linear transformation, kernel of this linear transformation, linear functional T. Now there is one result that kernel of a orthogonal complement of a kernel of a linear functional is one dimensional. So let me write the result. This you can also prove easily. Let T be a linear functional on a Hilbert space H, then kernel of T and orthogonal complement of the kernel of T is one dimensional. Okay. So we have got that kernel of orthogonal complement of a kernel of T is one dimensional. Now what will be this? So what will be the orthogonal complement of the kernel of? So M is the kernel of T. So orthogonal complement will be one dimensional. It will be spanned by some one vector. So what is in the orthogonal complement of this kernel? What is in the orthogonal complement of this kernel? So you can see that what is the orthogonal complement? Kernel T complement. What will be kernel T complement? So it will be also G in L2 minus 1 comma 1 such that G H is 0 for H in M or kernel of T, which is M. Right, so this is the orthogonal complement of the kernel. So G in L2 minus 1 comma 1. So this inner product is defined to be minus 1 comma 1. Note that this we can write. G is in, oh sorry, H belongs to kernel T. So for G belongs to, this is the function, real function note, integral minus 1 to 1 gx is 0. So this you can view as minus 1 to 1 gx dx, gx dot 1 dx. For G in kernel of T, right? So if G is in the kernel of T, then the linear function will be 0, so this will be 0, right? So therefore, this is the inner product of G and 1 is 0 for G in kernel of T, which is M, which implies 1 belongs to kernel of T complement, orthogonal complement, because inner product of 1 with any G in the kernel T is 0. So means 1 is in the orthogonal complement of the kernel. And as kernel of T parp is one dimensional by this result, so therefore this will be generated by this one. So kernel of T parp, this is the subspace generated by the vector 1. And note that 1 is in the L2 of minus 1 comma 1, because this is 1 is square integrable in minus 1 to 1. So this L2 of minus 1 comma 1, we have a direct sum decomposition, kernel of T, orthogonal direct sum, kernel of T parp. and kernel of T, this is M, so orthogonal direct sum, this is the space generated by 1. Now, so 1 is in the kernel of T part. Now, is this orthonormal? With respect, so note that, so what is the norm of 1? So norm of 1, so this is minus 1 to 1. So we want to find the orthonormal basis of the kernel T part, minus 1 to 1 mod 1 square dx to the power half. So minus 1 to 1 dx to the power half. So this is 2, so root 2. So we take this vector. So take this orthonormal basis, kernel of T part because now this is now orthonormal, right? Now what is the, so you want to, now what will be the projection of some element G in this space? So note that for G in L2 of minus 1 comma 1, the projection of G on kernel of T part, which is the span of this. So this is the orthonormal basis 1 by root 2 of the kernel T part is given by, so the orthogonal projection of G is given by so P over the kernel T part of G, so this is G inner product the orthonormal basis times the orthonormal basis. So this is the orthogonal projection. So this lies in the kernel T part. So what will be the orthogonal projection on kernel T? So therefore orthogonal projection on kernel T is given by, so P orthogonal projection on the kernel T of G is given by, because so then this will be G minus the projection on the kernel path. So this is the orthogonal projection on the, if it is in the PARP is given by this, then the orthogonal projection on kernel T is given by G minus the projection on the PARP. So G minus, this is the orthogonal projection on kernel T PARP is this. So this one. Now, so we have find the orthogonal projection for any vector G in L2 into the kernel T or M. Now we have to find the shortest distance between F and the subspace M. So there we need the projection theorem. It's saying that the shortest distance of any element in the Hilbert space is given by the distance between that element and the orthogonal projection onto that subspace. So this is the theorem, projection theorem. So this is, I am writing it in general for any closed convex subset. Let S be any closed convex subset of a Hilbert space H. Then for each x in H, there exists unique x naught in S such that the distance between x and x naught, so this is the norm, means this is the distance between x and S, is same as means attained at the point where x naught is the orthogonal projection. Infimum of all such x minus y, so that y is in S, and x naught, this x naught is the orthogonal projection of x onto the S. So the means it is saying that the distance is attained where it is the orthogonal projection. So x naught is the unique close point. So when S is closed linear subspace for each x belongs to S, let, we are denoting the projection to be x naught. So this is what we call the projection, means this theorem gives us guarantee that for x is in H, we have a unique x naught in the closed convex subset. So that unique point we are saying it to be the projection of x, where x naught is the unique point in S closest to x. And so this is the, for any x, the where the distance will be attained, that we call the projection, and projection we have calculated for okay, so here we have to find the, so basically this will be the distance between the point and the subspace will be given by the projection. It means distance between that point and the projection of that point onto that subspace. So here we have fx to be x square, and to find means distance between f and g, where so this is, we have to find the distance between f and m, right? So this will be given by, so as distance between F and M. This is the infimum of all such F minus G such that G is in M. And we have, by projection theorem, we have seen that this infimum is attained at the, so this is the distance between F minus the projection on M of F onto M. Right, so this is the unit point. So what is this projection of M, projection of F onto M? Means projection onto the kernel of T of this x square. So what is this formula? Projection of G on kernel of T is given by G minus G inner product with 1 by root 2 times 1 by root 2. So this is x square minus x square comma 1 by root 2 times 1 by root 2. So this is x square minus, what will be this? 1 by root 2 minus 1 to 1 x square into 1 by root 2 dx. X cube, so it will be 2 by 3. So if you calculate, what you will get? X square minus 3. So this is the projection of x square onto kernel of T or M. Therefore, distance between x square and M is given by x square minus projection of M of x square. So this is x square minus 1 by 3. So norm of 1 by 3. So minus 1 to 1. So this is x square minus 1 by 3 mod square dx. So x square will be cancel out, minus 1 to 1, 1 by 3. It is 2 by 9. 1 by 9 dx. So it is 1 by 3 and integral of this is 2, so square root 2 by 3. So this is the distance between x square and M, x square 2 by 3. So therefore which option is correct? So therefore option number is square root 2 by 3. Option number A is the correct one. Okay. Okay, so question number 33 is also completed. Any questions or doubt? Okay, so if not, we can stop for today. In the next week, we will again solve 2 problems from analysis or calculus. Yeah.
Okay, so let's stop for today.